Good evening, dear all. Welcome to this popular lecture series organized by ICTS JNP, the Coffee with Curiosity program. On this pleasant evening, we'll start yet another session, popular lecture series. To start with, I request our director of the Jawaharlal Nehru Planetarium, Dr. Guru Prasad, to address the gathering.
Ladies and gentlemen, good afternoon to all of you. I'll be as brief as possible. I don't want to come in the way of you and the lecture. Okay? Anyway, what an exciting and galvanizing subject. Really, that's what I was mentioning to Professor Bharat Ratra just now. The accelerating, expanding universe, dark matter, dark energy, and Einstein's cosmological constant. All of you know, from the time of Hubble, universe is expanding. People were thinking anyway that whether that expansion will come to a halt after some time and will there be a big crunch. That was the thinking, and sudden after that, people were somewhat puzzled by the accelerated expansion of the universe. And what is it due to? Dark energy, dark matter, and of course, cosmological constant is one of the most exciting things. And Professor Bharat Ratra from Kansas State University, all the way from there, Professor has come to enlighten all of us. I welcome you, sir. And this being yet another lecture of the KAAPI with Curiosity program, which is being organized jointly by ICTS of Bengaluru and JNP. And ICTS is represented by Professor Ajit Parameswaran. Welcome to you, sir. So, with these words, I welcome you all once again. Thank you, Professor. Thank you, Professor Ajit. And I would request Anand to announce the next one.
Now I request Professor Ajit Parameswaran to introduce the speaker of today's talk. Thank you.
Good afternoon. It's a great pleasure and an honor to welcome today's speaker, Professor Bharat Ratra. Professor Ratra is a physicist, a cosmologist who has made pioneering contributions to different aspects of cosmology and astroparticle physics. He's currently a distinguished professor of physics at the Kansas State University. So his work is very widely recognized. So he has made very important contributions to different aspects of cosmology. In particular, with Jim Peebles, he proposed one of the first, perhaps the first, dynamical dark energy models. And it seems that, I don't know how many of you are following, the last month, the DESI collaboration has come up with some very interesting results that suggest that perhaps the accelerated expansion of the universe is not due to a cosmological constant, but something more dynamical. And we are going through a very exciting field in the exploration of the universe. And Professor Ratra has made pioneering contributions to this endeavor. His work is very widely recognized. He is an elected fellow of the American Physical Society, the American Astronomical Society, and the American Association for the Advancement of Sciences. Of course, well before he joined the faculty of the Kansas State University, he grew up in India. He graduated from the IIT Delhi, and he went later to Stanford for his PhD. And he was as a postdoc at Princeton, Caltech, and MIT before joining the faculty of Kansas State University. And with these few words, let me welcome Professor Ratra for delivering this very exciting lecture.
Thank you for the very kind introduction.
1 minute to hand over a small memento. Sorry, I forgot.
Oh, thank you. Okay, I'll take a look at this after the talk. It's a great pleasure to be here, and thank you very much for the very kind introduction. So before I start, I just want to point out those cards. You're welcome to take them. And they're connected to this website, which has some really nice videos about global warming. And it's a useful thing to understand and to discuss with people because I think it's going to be a problem and it's already starting to become a problem. So I'm a cosmologist, and that means I'm interested in things that are distributed on very, very large scales in space and how these distributions change with time, how they evolve. And it's a very exciting time to be a cosmologist. This is because we have great telescopes in space and on the ground with big mirrors that are collecting many more photons, and so you can see much fainter objects. And you've all seen pictures from the James Webb telescope, and that's just one example. There are many other such telescopes. And these measurements of these data that these telescopes are collecting are reinforcing two very striking results. So the first one, which I'm sure most of you are familiar with, is that when we look at the energy budget of the universe now, we only understand 5% of what's out there, and that's atoms and molecules. The remaining 95% is composed of two different things. One's called dark matter and the other's called dark energy. And all we see are the gravitational effects of these two substances. We haven't directly detected them. So it's a very exciting time to be doing physics because 95% of the stuff out there is unknown, and so you have a lot to discover and understand. The other result that's getting reinforced by these observations is that it seems that quantum mechanics or relativity or both are incomplete descriptions of reality, and they need to be improved upon. And if this point gets established more by further observations, it's going to be a very profound result because quantum mechanics and relativity have been the foundations of physics for more than a century now. So I'm going to start over here, which is 10 minutes away from where I live in the middle of the US in eastern Kansas. And it's a nature preserve, and these are actually American bison. They're not cows. They've been restored here. And it's a very nice place to go hiking. So I have some questions for you, and you can put up your hands and answer them. So how many people have gone hiking more than 10 kilometers in their life? What about 100 kilometers total, integrated? 1, 2, 3, 4, 5, 6, 7. What about 1,000 kilometers integrated? Okay, so there's an upper limit you can access with your senses directly. I mean, maybe if you're really patient and you're old enough, you could probably hike 10,000 kilometers, but beyond that, it doesn't seem likely. Okay, next one, those of you who have hair, I want you to reach up and grab a strand of your hair with your fingers and just feel it. So is that kind of the thinnest thing you could feel with your fingers? Or are your fingers sensitive enough to feel something thinner than that? I mean, that's probably the limit, right? So that's maybe about 10 to the minus 4 meters in diameter. Typically, human hair is maybe 100 microns or so. So there's a range over which you can directly access length scales. And so this is in meters here. Should I be moving this a little bit? Is this clear enough for the mic? Put it further up. Okay. Okay, so this, yeah, maybe this is better. So this is in meters, and a typical human somewhere about 1.5 meters. And directly with your senses, you can probably reach down to 10 to the minus 4 meters and maybe up to 10 to the 5 or 10 to the 6 meters. But there's a lot of things going on much, much larger scales and much, much smaller scales. And I want to kind of discuss how one builds intuition. The way you build intuition about reality is fundamentally different when you can access these scales directly with your senses. You can't do that on larger scales or smaller scales, excuse me. So you can, if you're clever enough like Newton, you can drop apples or you can collide balls and you can figure out the inverse square law of gravity and conservation of energy and conservation of momentum and Newton's second law of motion. And you can do that on macroscopic scales over here. But you can't walk out to the moon or you can't start taking apart an atom with your fingers. And the way you study physics on these scales and these scales is you collect stuff that comes from these objects. So if you're looking at a galaxy, you have a telescope, you collect the light, and you store that light as electronic signals on your computer. And then you build a mathematical model and use that model of this object and make predictions of what you should be seeing. And then you compare those predictions to those electronic signals in your computer. And that's how you build up intuition over here. And down here, you can use microscopes or particle accelerators, and you collect something like light, or maybe in some other cases, some charged particles, and compare them to predictions you make from a mathematical model. And you build up intuition there very, very differently than you build up intuition here. So even a 3-year-old child can develop intuition about Newtonian physics if the child is intelligent enough and observes things. But it's very difficult for that child to build up any intuition about relativistic physics or quantum mechanics. And so it's probably not surprising that things are very, very strange when you talk about relativity and quantum mechanics, because your intuition has been completely developed over here, unless you're trained as a physicist. And so people don't usually appreciate how large this range of length scales is. So I'm going to walk out, and I'll start from the human scale. And this guy, you probably recognize him. Instead of the old-fashioned system of meters, I'm going to use him as a length unit. So we'll be measuring things in terms of Einsteins. So an Einstein is roughly 2 meters. And it's useful to do this also in terms of masses and in terms of time scales or ages. But I don't have time for that, so I'll just be doing this in terms of length scales. And for those of you who are interested, there are 2 very, very nice videos. You could probably search on Google and find them, or whatever search engine you use. One's called The Powers of 10 by the Eames brothers. That's E-A-M-E-S. And this is from, I think, from the 70s. And they go over this whole range of length scales with different examples. And the American Museum of Natural History has a similar sort of video, which is, they're both pretty short. I think they're 10 or 15 minutes, and they're very instructive to look at. So we'll start out on human scales and then try to compare him to this object. And a picture like this has only become possible in the last 60 or 70 years since we've had satellites with cameras. This is the Indian Ocean, India's over here. And one way we can do this is we can build a tunnel from the North Pole to the South Pole and build a base here. And then you can go and collect 6.5 million Einsteins, place the first one at the South Pole, the next one is shoulders, the next one is shoulders, and so on. And if you have 6.5 million of them, then you'll cover the diameter of the Earth. So 6.5 million is roughly 10 million. So to go from a human scale to the scale of a small planet is a factor of 10 million. And that's quite a big factor. 10 million is a big number. We can go out to our sun and do the same thing. I mean, you can think about, at least as a thought experiment, building a tunnel from the North Pole to the South Pole. And if you have 100 Earths piled one on top of the other, you'll cover the diameter of the sun. So the sun is a factor of 100 bigger in linear size than the Earth. And so compared to an Einstein, it's 700 million Einsteins. And we can go another step, another factor of 100, and look at the Earth-Sun distance. And this is not to scale, but the Earth's orbit is approximately, very roughly, a circle around the sun. More precisely, it's an ellipse, but you could average that out over the course of a year. And if you want to cover the radius of that orbit, you can line up 100 suns in a row, and it'll go from the surface of the sun to the Earth's orbit around the sun. So it's another factor of 100. And in terms of other units, like in terms of meters, you're coming with many, many powers of 10, and that makes it very inconvenient. So people who study the solar system use a new length unit. They use 2 different length units. So one's called the astronomical unit, or the AU, and that's the radius of the Earth's orbit around the sun, averaged over the course of a year. The other unit is to make use of the fact that light has perfected cruise control. So how many of you have cruise controls in your car? you can just push a button and you can set the car speed and it'll go at that constant speed. So if you know the car is going at 60 kilometers an hour and you know you've gone for 1 hour, then you'll know you've covered a distance of 60 kilometers. And light has perfected cruise control. It always travels at exactly the same speed in vacuum, and that's a pretty huge number. It's 3 times 10 to the 8 meters per second. And in this case, it's a little bit more useful sometimes to think about how many feet per second light goes at. So a meter is roughly 3 1/3 feet. And so this is 10 to the 9 or 1 billion feet per second. So in 1 second, light goes 1 billion feet, or it covers a foot, which is about this distance in a nanosecond. So it goes very, very fast. And so instead of using 1.5 into 10 to the 11 meters, we'll divide that by the speed of light and get 500 seconds. And so if I tell you that the Earth-Sun distance is 500 seconds, that means that's the distance light travels in 500 seconds, and it's 1.5 into 10 to the 11 meters. So I can call these light seconds if you want, but I don't have to. I can just give you the light travel time, and that's 500 seconds. So that's a pretty long time compared to how long it takes light to cover 1 foot. And it's kind of really interesting to think about what's happening. So when you're looking at the surface of the sun, and if you look at the sun, you should be really careful and use protective equipment, otherwise you'll damage your retina. But when you look at the sun, you're not seeing the sun in the present. You're seeing the sun as it was 500 seconds ago in the past. You never see anything in the present. Even in this room, when you look at your friend sitting next to you, you're seeing your friend 2 nanoseconds in the past. And your brain kind of doesn't care about 2 nanoseconds, so usually you assume you're looking at that person in the present, but that's not true. You're looking at that person in the past. And this becomes more and more important when you go over larger distances. So it's 500 seconds to the sun. And we can walk out further. So we can go to the nearest star to the sun, which is Proxima Centauri. And that's another factor of 10 to the 5 in distance scales. So in meters, it's 4 times 10 to the 16 meters. So in light travel time, it's 4 years. So when you look at Proxima Centauri through a telescope, you're seeing that light as it was when it left Proxima Centauri 4 years ago. And it traveled in a straight line and came into your telescope and then hit your retina and got converted to an electronic signal and turned into an image in your brain. So that's a pretty big time, and if you think about this in terms of AUs, it's about 200,000 AUs. So it's getting to be pretty inconvenient to even use AUs when you're talking about distances between stars. And so people actually use a different unit there, which is called the parsec. And that's spelled out this way. It's parallax of an arc second. It's an abbreviation for parallax of an arc second. And parsec itself is abbreviated PC. And this is a kind of unusual unit because it's had historical significance. And we can talk about that later if people are interested. But the way it's defined now is you take your observer and send her out with a telescope far away enough from the Earth-Sun system. So this huge distance of 1 AU, the distance from the Earth's orbit to the Sun, this 1 AU subtends a very tiny angle of 1 arc second at the observer. So an arc second is a very tiny angle. To go around a whole circle, you cover 360 degrees. And each degree you can split up into 60 arc minutes, and each arc minute you can split up into 60 arc seconds. So there's roughly 200,000 arc seconds in a whole circle. And so when this observer is far away enough that this huge distance here, this linear distance of 1 AU subtends an angular distance of 1 arc second at her, she's said to be a parsec away from the Earth-Sun system. And probably the most convenient thing about this plot is to realize that a parsec is 3 1/4 years or 3 1/4 light years. So light takes 3 1/4 years to travel a distance of 1 parsec. And so the nearest star, Proxima Centauri, is roughly a parsec or a parsec and a third away from us. And to give you some concrete numbers here, the Earth-Moon distance is roughly 1 1/3 seconds from us. So when you're looking at the moon, it takes light 1 1/3 second to get to us. And that's the furthest we've sent humans. Pluto's orbit maybe can be used to characterize the size of the solar system, and that's 40 AUs. Or in terms of light travel time, it's 6 hours. And the furthest humans have sent anything are the 2 Voyager missions, and these numbers, these Voyager missions were launched in 1977, and these numbers are from 2017, the 40th anniversary, so they've gone a little bit further. Voyager 1 was 140 AUs then, or light travel time was 19 1/3 hours, so that's pretty far away. But we can step out even further and look at this object. This is the object we live in, the Milky Way galaxy. And if we can turn down the lights, maybe it becomes a little bit clearer. But the best way to look at this is to go on the web. And this is, you can find this on the European Southern Observatory page. It's the European Southern Observatory Milky Way galaxy, or European Southern Observatory galaxy, and you can zoom in. And this is a collection of a few, maybe 100 billion or 200 billion stars. And the typical star here, so the sun is about twice as massive as the average star. And maybe, so this is with modern technology, this is with stuff from 60 or 70 years ago. And this is probably the easiest picture to discuss, this artist's impression of the Milky Way galaxy. So it's a disk, and when you look at it from the top or the bottom, it's like a frisbee, and you can see the spiral arms there. And maybe we should start with the diameter of the disk. So it's 50 kiloparsecs, 50,000 kilos, 1,000, and 1 parsec is 3 1/4 years. So if you want to convert this into light travel time, you multiply 50,000 by 3 1/4, and you get about 160,000 years. So if you started out here and tried to cross this, and if you could travel at the speed of light, which you can't, you have to be massless to do that. But something traveling at the speed of light would take 160,000 years to cross this. And you can compare that to 500 seconds to the sun, or 4 years to Proxima Centauri from Earth. And so this is a very, very huge object, about 200 billion stars. And the fact that it's a disk tells us immediately that something's going on, because these stars are pretty massive, and Newton's inverse square law of gravity tells us that they're going to be pulled together unless there's something that resists that. And so the thing that's preventing this disk from collapsing completely down to the center over here is the rotational motion of the stars. They're systematically rotating. If you're looking at it from the top, they're systematically rotating in the disk. So they have kinetic energy, and they have angular momentum, and that angular momentum is conserved. And it's the same thing as a satellite going around the Earth. It doesn't fall to the Earth. So there's the nucleus of the disk of our galaxy. The sun is about 1/3 of the way out, and there's a bulge here where there's more stars. And these stars are not systematically rotating, but they have velocity, and they're moving around randomly. That's why they don't collapse inwards. So the sun's 1/3 of the way out from the center of the disk. And right at the nucleus here, we have a black hole. And this is a pretty puny black hole on the scale of black holes at the centers of galaxies. It's only about 4 million times as heavy as the sun. And this disk is embedded, this is the shiny stuff, it's embedded in a halo that's a spheroidal, and maybe 10 times the linear scale of the bright shiny disk. And there's a lot of dark matter in that halo. That's where a lot of the mass is. And in that halo, there are these globular clusters. These are collections of old stars, hundreds of thousands of very old stars. And they've been near each other and being pulled together gravitationally for quite a long time. So they're distributed in a spherically symmetric way. I mean, that's why the Earth is roughly spherically symmetric, because it started out in a form that gravity could deform it. And gravity always wants to minimize the energy, and it prefers to turn things into spheres unless there's some other energy involved. And so these guys are orbiting in this three-dimensional space around the center of our galaxy. And you can also see a black band here, and this black band has as many stars as the shiny parts of the galaxy. There's just a lot of dust there, like the dust you sweep up at home or you vacuum up. And this dust either absorbs the light from the stars, the visible light, the light that you can see with your eyes, or it scatters it out of the line of sight. And so when you're looking at it, that light from the stars that are embedded in the black here, they don't reach you. And because some of it is absorbed by the dust, that dust is going to get heated up because that light carries energy, and then it's going to start radiating because it gets hot. And we know from the second law of thermodynamics that the energy that it puts out is going to be of lower quality than the energy that it absorbs. So instead of sending out short wavelength visible light that we could see with our eyes, it's going to send out longer wavelength infrared light that's not visible to us. But if you had an infrared telescope and you looked at this black band over here, it would be very, very bright. So depending on what wavelength you use to study a galaxy, the shape of the galaxy is very, very different. And you can see pictures maybe of 20 different wavelengths of the same galaxy if you go search on the web. And you have to be a little bit careful what you find on the web, and just make sure you go to reputable sites like observatories or Planetarium or Scientific American or Discover, and make sure you look at things that are really true and not made up. So this is our Milky Way galaxy. And so those of you who haven't seen this, there's probably some amateur astronomy groups in Bangalore, and you should try to find out when they take you out for observing. And you can see this, you can see these globular clusters, and they're very, very impressive, and they're well worth seeing. And you can also see this guy, which is the Andromeda galaxy. It's another spiral galaxy. It's at a slight angle to us, so you can see the spiral arms, and you can see the dust bands, and you can see the central bulge. And it's a little bit bigger than the Milky Way, so maybe 200,000 years to cross it at the speed of light. So it's about 750 kiloparsecs away, and if you turn that into light travel time, it's 2.5 million years away in light travel time. So when you look at Andromeda, that light left Andromeda 2.5 million years ago, and it traveled in a straight line, and it hit your retina and turned into an image of Andromeda. And you can actually see this with your naked eye, not in this kind of resolution, but you can see Andromeda at certain times of the year. So this is a really interesting time scale relative to human evolution. Probably the most famous hominin fossil is Lucy from Ethiopia. And she apparently climbed up a tree approximately 3.18 million years ago to escape predators, and she apparently fell asleep in this tree and fell out of it and died 3.18 million years ago, which is not very different than the time that the light you see from Andromeda now left Andromeda. So this is our nearest neighboring big galaxy. So galaxies have masses. This is probably 200 billion stars like the sun. And so they're very heavy, and they have strong gravitational fields. And sometimes they come close together and they start pulling on each other, and they collect other galaxies. And these objects are then called clusters of galaxies. And this is the nearby portion of the Virgo cluster, the central portion of the nearby Virgo cluster. The time scale to cross this at the speed of light, so it's about a few megaparsecs. M stands for a million. And this is a few megaparsecs, so you multiply that by 3.25, and so maybe it's 7 or 8 million years to cross this at the speed of light. And this is just the central region. You can probably see as many as 2,000 galaxies here if this is printed at the resolution of the image that I had. And every single one of these dots is a galaxy. There are no individual stars. So you can see some in the foreground. You can see spiral galaxies and elliptical galaxies. And the scale here is maybe 7, 8 million years to cross it at the speed of light. And each of these guys has 200 billion stars. Some of them have more. Excuse me. This is a very heavy and huge object, but it's very insignificant on the scale of the universe. So this is the bigger chunk of the universe. And this is taken, I'll go back to this image for a second. So there's dust here, and so if you want to see the extragalactic sky, it's better to look up over here. And we're looking at an image of this area up here with kind of part of a circular wedge. And it was taken by these guys, Shane and Vertanen, in the early 60s with a regular telescope. And they didn't have CCDs then like we have in the phone, so they put glass plates there with emulsion on it at the focus. And then they developed them. And they didn't have laser scanners or computers, so they figured out the positions of 400,000 galaxies by hand using paper and pencil. So the scale here, so those of you who are students can kind of think of this when you're worried about your homework or upset about your homework, to sit there by hand with paper and pencil to figure out the angular positions on the sky of 400,000 objects from glass photographs. So the scale here, it's about 300 megaparsecs. So to turn that into light travel time, it's 300 million. You multiply by 3.25, so it's about 1 billion years or 1 billion light years. So traveling at the speed of light, it'll take 1 billion years to cross this. And this also is just a small part of the universe. So if you look at this carefully, you can see 3 kinds of structures. You can see clusters of galaxies. This is the Coma cluster, and it's just a few pixels. It's about 120 megaparsecs away from us towards the North Galactic Pole. You can also see other clusters of galaxies, and you can see voids, these black regions where there's no bright galaxies. And these are black because, not because there's dust there, they're black because there are no bright galaxies. And the bright galaxies tend to, so if you want to think of this geometrically, you can think about soap bubbles in your basin. The bright galaxies tend to be on the surfaces of the bubbles, and they avoid the interiors, and the interiors are called the voids. And where 2 bubbles come together, there's an enhancement in the number of bright galaxies, and from projection and the way we look at it, they look like filaments. And so they stand out more. You can see these one-dimensional structures. And these are where 2 bubbles kind of meet together, and you have an enhanced number of bright galaxies. And the filaments tend to drain towards the clusters. So there's a lot of structure here. And a distribution like this is said to be anisotropic, which is a bit of jargon. So when you say something is isotropic, that means you're standing in one position and you're looking around you in all directions, and above you and below you and in front of you and behind you. So if you look in this room and you look to your right and you look above you, you don't see the same person. This room is very anisotropic. So if we go up 100 kilometers off the surface of the Earth and we look towards the north, you'll see the Himalayas, and you look towards the west, you'll see the ocean. And the surface of the Earth is very anisotropic. The solar system is very anisotropic. You look in one direction, you see the sun, and you look in another direction, you don't see an equally big nearby star. The Milky Way is very anisotropic. You look towards the center, you can see that bulge of the Milky Way. And if you look that way, you don't see as many stars, you see many more this way. So even on scales of tens of millions of light years, it's very anisotropic. You look over here, you don't see any bright galaxies. You look over here, you see thousands of bright galaxies. So maybe it's not surprising because this room is anisotropic and everything else is anisotropic up to this point. But the thing that's surprising is that when you go another factor of 10 or so, it becomes very isotropic. It looks the same no matter what direction you look in. And for now, this is the largest scale structures we can see. This was taken by the Planck satellite that was launched by the European Space Agency. And they launched this with microwave detectors on it. And they're looking at bumps, or they're looking at the cosmic microwave background radiation. So microwaves are part of the electromagnetic spectrum. Their wavelength is much, much larger. It's fractions of a millimeter compared to the visible light spectrum, which is maybe 12 or 13 orders of magnitude smaller than that, shorter wavelength. And it's the same if you have a microwave at home. It's the same kind of electromagnetic radiation used to cook food. And so they can use this, they can collect the light that comes from the leftover light from the Big Bang. And so the way to kind of think about this is to think about the satellite here surrounded by a big ball, and it's measuring the temperature on the walls of that ball. And I've sliced that ball from the North Pole to the South Pole and spread it out. So if you want to reassemble it, you take this edge and join it up with this edge and fold it up around you. So you're sitting there and collecting the photons and looking at their spectrum. As you collect this, there's an instrument that looks at the spectrum of these photons of the electromagnetic radiation. And some of them so once you know the color of the photon, from that you can use results from Planck's formula, and you can use results from Boltzmann's relation to figure out the temperature of the photon. And so this is measuring the temperature, and they're showing the temperature here in terms of redder, hotter temperature and bluer, colder temperature, which is a little bit unusual for a physics plot, but that's what it is. And so the first thing you might be interested in is the average temperature across the whole surface that they're looking at. And so if you average this temperature, it turns out to be about 2 3/4 Kelvin. So the Kelvin is the absolute temperature scale. So this room is roughly about 300 Kelvin now. And at 0 Kelvin, all motion stops except 0-point uncertainty motion. So this is very, very cold radiation. But once you have the average, then you can ask about the temperature difference between the red hot spots and the blue cold spots. And that's roughly 30 microkelvin, or 30 millionths of a Kelvin. So if you want to compare the temperature difference to the absolute temperature, you divide 30 millionths of a Kelvin by 3 Kelvin, and you'll get roughly 10 to the minus 5. So the anisotropy is 1 part in 10 to the 5 when you go from a red hot spot to a blue cold spot. Or in terms of percentage, this is isotropic to 0.001% across the sky. So it's very, very isotropic. It looks the same over here to over here, unless your experiment is precise enough to measure differences of 0.001%. While over here, when you go down to scales of tens of millions of light years, it's very anisotropic. It's very bumpy. It looks different in different directions. So these are two very important facts about reality. That on small scales, the distribution of matter and radiation is spatially anisotropic. I have to take out a demonstration that I didn't earlier, so I'll do that while I'm talking. It's different in different directions, but when you get out to larger scales, the matter and the radiation, the matter and the light, is isotropic. It looks the same no matter what direction you look at in a statistical sense. And the differences are only 1 part in 10 to the 5 or so. So I'm not going to go into these much in any more detail. But if you're interested in how physicists reconcile this with their theoretical models, you might want to search on reputable sites like Wikipedia or Scientific American for the inflation model of the very early universe, and that's how physicists make sense of these two facts about the real world. And inflation is consistent with all the measurements we have, but the measurements are not precise enough to really establish inflation as being true right now. But hopefully in the next decade or so, we'll get more precise measurements and we'll know whether inflation happened or it didn't happen. Okay, so the next fact is even more difficult to appreciate, and this is that the universe expands. And so if the universe is expanding, that immediately implies we've got a measuring device that is not also expanding in exactly the same way. And one thing we could think about is why that happens. So I have a little measuring device here. It's a centimeter ruler. And if we think the universe is expanding and we think this is not expanding, it's probably useful to understand why we think that. So this guy has some mass, or I don't have another object, so I'll just use this as my object. And the Earth has some mass, and Newton tells us that if I don't support this, the Earth is it creates a gravitational field and pulls this mass towards it, and this creates a gravitational field and pulls the Earth up also a little bit. But the Earth's much more massive, so the Earth hardly moves, and so we see this moving a lot. So that's one force that's really important on macroscopic scales. It's Newton's inverse square law of gravity. So if we have two masses, the force between these two masses is proportional to each mass. It's also inversely proportional to the square of the distance between them. So if we double the distance, the force goes down by a factor of 2 squared, or 4. If we triple the distance, the force goes down by a factor of 3 squared, or 9. And the other thing it's proportional to is Newton's big G, Newton's gravitational constant. So there's another force that's also important, and that's the electric force. So the gravitational force is always attractive. Gravity always pulls. But the electric force comes in two varieties because there's two different kinds of charges. So as an example, we can think of the electron, which conventionally has negative charge, and then the proton conventionally has positive charge. So if we bring two protons near each other, the electric force is going to push them apart because like charges get pushed apart. And the same thing happens if we bring two negatively charged electrons together, they get pushed apart. But if we bring a proton and an electron together, they'll get pulled together. So the electric force can be attractive between unlike charges, and it's repulsive between like charges. It's also an inverse square law force, and the relevant law is called Coulomb's law there. So again, if you double the distance, it goes down by a factor of 4. So both of these are inverse square law forces. So if we take two protons, they're going to be pulling on each other gravitationally, and they're going to be pushing on each other electrically. So we can calculate the ratio of the electric push to the gravitational pull. And I don't know if anybody's done that. Some of you are physics students, I guess. So does anybody know the ratio of the electric push to the gravitational pull between two protons? So it's a huge number. It's 10 to the 36. So the electric force that's pushing these guys apart is extremely strong compared to the gravitational pull. Gravity is a very, very weak force. So I have a bunch of questions for you. So you all have masses. Are you pulling each other together gravitationally? Those of you who think you are pulling together gravitationally, put your hand up. Okay, so those of you who think you're pushing each other gravitationally, put your hand up. Okay, so 3 or 4. And so half of you didn't put your hands up. What do you think's happening with the gravitational force? Are you just very shy? Okay, so you're made up of charged particles. You're made up of electrons and protons. Are you pulling each other electrically? Who thinks you're pulling each other electrically? 1, 2, 3, 4, 5, 6. Who thinks you're pushing each other electrically? 1, 2, 3, 4, 5, 7, 8, 9, 10. So what do the rest of you think? You're neutral. You're made up of atoms. So you have the atom, there's a central core that has the protons with positive charge and then an equal number of electrons. So your protons are pushing your neighbor's protons away electrically, and they're pulling your neighbor's electrons to you electrically, and those cancel out, so you're not affecting each other electrically. Unless you bicycled in here or you combed your hair very vigorously, then you'd have static charge, and then you'd be affecting each other electrically. So on small scales, on the scales of these guys, it's all made up of atoms. So atoms have these big electron clouds. The electron clouds are a factor of 10 to the 4 bigger than the nucleus of the atom. And so they don't like each other for the neighboring atoms because the electrons are much closer together to each other. And so they're trying to push each other apart. But if you're in a solid, there's atoms beyond you and in front of you and above you and below you. So these guys, if they're pushing this way, they're getting pushed this way and they're getting pushed this way, and they can't go anywhere. And that's why they make this guy rigid, and it's a very, very strong force. It's much stronger than gravity. So gravity does not affect the distance between the atoms. So it's actually quite amazing because you're mostly empty space. The nucleus of the atom is a factor of 10 to the 4 times smaller than the electron cloud, and everything in between there is empty space. So you're empty space, the chair you're sitting on is empty space, the walls are empty space. And it's amazing you don't fall through the chair, and the only reason that's not happening is because the electrons don't like each other. But when you get out to larger scales, you're made up of atoms, and bulk matter is neutral, so the electric force gets screened. And so when you start scaling up from your mass to the mass of planets or the mass of stars, the gravitational force gets stronger and stronger. So on larger and larger scales, gravity is more important. And on smaller and smaller scales, the electric force is more important. So electric force gives us rigidity, and gravity is the relevant force for cosmology because it's the most important force on large scales. So if we're going to talk about cosmology, we need to discuss what gravity does. And we know Newton's inverse square law of gravity, but Newton made a couple of assumptions. He assumed space was fixed and time ran uniformly. And then almost 300, 400 years after Newton, Einstein realized that he could provide a better description of reality if he allowed space and time to participate dynamically in what was happening in your physical system. So if you're colliding two masses, you don't do that in a fixed space with a uniform time, but you allow the space to respond to the masses moving, and you allow the time to respond. And the general description of this is called the general theory of relativity. And it's described in terms of mathematical equations, and this holds on scales that you cannot directly access through your senses. So it holds when things are moving at speeds very close to the speed of light, and we have no experience of what happens when things move at the speed of light. And it holds in very, very strong gravitational fields. It also holds on very, very large scales, on scales where the universe is isotropic. And we can't directly sense those scales. So the only way we have to build up intuition about the general theory of relativity is to solve linear partial differential equations and make predictions for what we'd see. And so the predictions are solutions, they're mathematical solutions, but usually you have to turn that into English to describe them to people, and that translation is very inexact. So I'm going to try to turn those solutions into English descriptions. So I'll start out with a very simple demonstration here, or an analog. So I have a space here. It's a one-dimensional space because I can just draw an origin over here and then measure distances from here. And you're supposed to ignore the width of this. And so if I know how far I'm here from here, I just need one number, and that'll tell me how far I am. And I've drawn a wave on here, and I'm also going to have my measuring device here that's held together by the electric force. And what general relativity is going to do is it's going to create more space. So it looks around and sees regions where there's less mass than usual, and it'll create more space. And as it creates more space, we can look at what happens to the wavelength. So the wavelength is the distance between the peaks, or the distance between the troughs, which you can measure with your measuring device, which is not affected by the gravitational field created. So it creates more space, and that wave lives in it, and so the wavelength gets bigger and bigger. So in physics, blue light is shorter wavelength, and red light is longer wavelength. So if you allow the space expansion to go on long enough, you start out with blue light, it could turn to red light or infrared light if the universe expands. If it contracts, it goes the other way. Red light becomes blue. Longer wavelength light becomes shorter wavelength light. So this is not a very accurate demonstration. So first of all, general relativity doesn't go to the ends of space and start pulling. There are, in the simplest model of cosmology, there are no ends to space, it's infinite. And this doesn't happen just in one dimension, it happens in all three dimensions. So we're living in a three-dimensional space here. So you can set up a coordinate system, maybe you'll set it up in that corner over there, and that's your origin over there. And you'll have one vertical axis and two horizontal axes. And then to measure the position of this point here, I'll have to measure this distance here, and then measure the distance up from the floor and measure it from the other axis. So it's a three-dimensional space. So space is three-dimensional. So we can go on to this, which is just this demonstration in terms of pictures. So we start out at an earlier time, and the exercise band is smaller, and as time gets bigger, the exercise band gets bigger. And you can draw these waves on your exercise band and take your ruler and actually measure them. And you'll see that the wavelength is proportional to the size of the exercise band, in this case, the distance between the two hands. And we can call this roughly the size of the universe, or at least the size of a local part of space. And physicists use the term scale factor, and they use the symbol A, which is a function of time, to describe that. So very loosely, the scale factor here is the distance between the two hands, and as time goes on, the scale factor gets bigger. This is the present universe, and this is the wavelength now that we would measure with our telescope and our diffraction grating. This is the wavelength at the time that object emitted the light, and that was the size of the universe then. And it's pretty easy to see that the wavelength, the distance between the two peaks or the two troughs, is going to be proportional to the size of the exercise band. So lambda gets redshifted. You go from shorter wavelengths to longer wavelength. And astronomers don't like talking about the scale factor, so what they prefer is something called the redshift z, which is defined through this equation here. 1 plus z is equal to the value of the scale factor now compared to the scale factor at the time when that light was emitted. So if you emit the light at the present time and then absorb it and study it, A of t would also be A of now. So A now divided by A now would be 1, and Z would be 0. But as you go back and emit the light earlier, A of t would be smaller than A of now. And so the denominator is smaller than the numerator, and so this would be bigger than 1, and that would mean Z is greater than 1. So Z increases as you go back in the past. As you move forward, the time increases, and the scale factor increases, and the wavelength increases. So this is the expansion of the universe. There is no preferred center. So the guy who first saw this was Slipher, and this is the telescope he used for this. It's at Lowell Observatory, which is about 80 kilometers south of Grand Canyon in Flagstaff, Arizona. So if any of you have a chance to go to Grand Canyon, you should go to Lowell Observatory and see this. So he pointed this telescope at galaxies outside the Milky Way, and he had diffraction gratings, and he broke up the light into its wavelengths, and he could form the ratio of spectral lines. He could realize that certain atoms were creating the spectrum he was seeing, and he compared the wavelength that he created from those atoms in his lab to the wavelength he was getting through this telescope, and he found that the wavelength he was getting through this telescope was redshifted. So he did this in 1912. And the next step, okay, before I get to the next step, let's just talk about this a little bit. So all of you have probably experienced this Doppler effect with ambulances or fire engines. So as it's coming towards you, the sound pitch goes up and the wavelength gets shorter. As it's moving past you, the sound pitch goes down and the wavelength gets longer. And that's the Doppler effect. So this is another manifestation of the Doppler effect. It's not exactly the same as the one from sound, and it's not exactly the same as caused by the physical motion because of the ambulance moving past you, but it's also a Doppler effect. And so he was seeing things that appeared to be moving away from him. And so one explanation could be that Slipher ended up in the position now where in the past there was this huge explosion and he was seeing the remnants of this explosion move away. But that's not the correct description of what's happening. Actually, what's happening is that every point in space is moving away from every other point in space. And to appreciate that, let's just start with a simple example here. So maybe I'll start with this demonstration over here. So like I said, general relativity on very large scales tells us space is being created and that space is spreading out and has to move apart. And everything that lives in that space has to go along with it. The galaxies themselves, which are the ping pong balls here, they're well described after they're formed in terms of Newtonian gravity, and they don't change in size significantly. While they're forming, they get stretched also, and so part of them don't collapse. But once galaxies are formed, the Einstein space creation process does not affect them. And so what's happening is that space between the galaxies is getting bigger and bigger, but the galaxies themselves don't get stretched. So if we have a flat three-dimensional space, and that's an example shown over here. So there's one axis here, one axis here, one axis here, and I've got a little piece here that's a three-dimensional piece. And I've got chocolate chips here, and I'm going to let the yeast rise, and everything's going to spread apart. And these chocolate chips are going to be my galaxies. So I'm going to ask my observer so first of all, this can't be a flat universe that's consistent with the observations, because if we go to the edge and look out, the outside will look different than the inside. And so it's got to be anisotropic, but I told you everything is isotropic on large scales. And so the way you make this isotropic is you send it out to infinity, send the edges to infinity in all three dimensions. So it's in the two-dimensional analog, it's like the top of this table. So if you walk to the edge and look out, it looks different than when you look in. And so the way you make it isotropic is you send the edges to infinity. So you send the edges out to infinity over here. And so you'll have an infinite number of chocolate chips, and you can put an observer on each one if that was possible, and ask them what they see as the yeast expands and keeps expanding. And every observer will tell you, if you ask the one on one what she sees, she'll tell you she sees every other galaxy move away from her. You ask the one on three what he sees, he'll tell you he sees every other galaxy move away from him. So the fact that Slipher was seeing galaxies move away from him didn't mean he was at the center of the universe. This is actually the correct description. An observer on Andromeda would also see every galaxy move away, except the really nearby ones. And we can discuss that later. But all galaxies are moving away from every observer. And so the Big Bang is actually at a point in time in the past where you have an infinite space. And every point, every one of the infinite points in that infinite space starts moving away from every other one of the infinite points in that infinite space. And the distances between them gets bigger and bigger, and the infinite space gets bigger and bigger and bigger. And that's the Big Bang in the expanding universe. So in this three-dimensional case, you're going to get expansion in 3 dimensions. So in each dimension, each length expands in proportion to the scale factor. And the expansion has got to be isotropic, so it's got to be the same in each of the dimensions. So if you want to know about the volume is going to go like length cubed, and so the volume is going to expand in proportion to a cubed. And this uniform expansion, that the increase in distance is proportional to the initial distance, is just Hubble's law. And that's the law up here. So there are a couple of important things after Slipher's observation. One actually before Slipher's observation, and the one after it. We'll start with the one after it, which is Hubble's observation. So this is Hubble, and this is the galaxy, the telescope he was using on Mount Wilson at the Hale Observatories. It's now called the Hale Observatories. It's in the San Gabriel Mountains, just north of the Los Angeles Basin in California. And it was a bigger telescope than the one Slipher had. It had a bigger mirror, it had a 100-inch mirror. And so he could collect light from much fainter objects, and he could actually resolve individual stars in these galaxies Slipher was looking at. And he saw some of these stars were pulsating, they were variable, they're getting brighter and dimmer. And he was able to identify some of them as Cepheid variable stars. And Cepheid variable stars are very, very useful stars. Probably the most famous one is Polaris, the North Pole star. They pulsate, and they pulsate extremely regularly. And they're very valuable because of a discovery Henrietta Leavitt had made, I think in 1907. She was based at the Harvard-Smithsonian Observatory in Cambridge in Massachusetts, where a lot of the astronomers would send the glass plates with the emulsion that they developed to store. And so she had access to many, many, many pictures of the same region of the sky, and she could see that there were stars that were pulsating. And some of these stars were nearby enough for her to get distances to them through triangulation and other methods. And she realized that they were pulsating very, very regularly, and their pulsation period was proportional to their distance from us. So if you know that, so you can measure the pulsation period of stars that are too far away to get direct distances to, and then once you get the pulsation period, you get the distance to those stars, and so you can figure out the distance to the galaxies. And so Hubble measured distances to galaxies that Slipher had used Doppler formulas to measure the recession speed. And he had found that the distance was proportional to the speed of recession. So a galaxy twice as far away would be moving twice as fast from us. A galaxy 3 times as far away would be moving 3 times as fast. And this constant of proportionality is called the Hubble constant. And it's got strange units because astronomers use strange units for some of these things. They measure the recession speed in kilometers a second and the distance in megaparsecs. But physically, this is distance over time, and that's distance. So the two distances cancel out, and it's 1 over time. So the Hubble constant has dimensions of 1 over time. But because they use kilometers per second there and megaparsecs here, it's got units of kilometers per second per megaparsec. And this is my favorite value. It's around 68. And people have questions. We can talk more about that later. And this is a demonstration of Hubble's law. This is a famous plot. It's from the Hubble Space Telescope. One of the reasons the Hubble Space Telescope was built was to more precisely measure Hubble's law and Hubble's constant. And the person who led that group, that key project, was Wendy Friedman. And this is the plot from the 2001 paper. So the speed at which the galaxies are moving away from us in kilometers per second here is on this axis. This is 10,000, 20,000, 30,000. And the distances on this axis here, you can move them up over here. These are residuals, which we won't discuss. So that's 100 megaparsecs, that's 200 megaparsecs, 300 megaparsecs. So a galaxy 100 megaparsecs from us is moving away at about 7,000 kilometers a second. A galaxy 200 megaparsecs from us is moving away at about 14,000 kilometers a second. And the red solid line was Hubble's law. The recession velocity is linearly related to the distance from us. It's linearly proportional. And the Hubble constant then was about 72. Now I kind of favor about 68. And so that's the expansion of the universe. And so how much time do I have left? Okay, I'll try to go a little bit faster. So we have 3 different geometries we discussed. I can't draw you them in 3 dimensions. So I talked about the flat geometry over here, and it's got to extend out to infinity, and it's got 0 space curvature. And likewise, we got the balloon geometry, the curved geometry, and that's 2-dimensional also, because all you need is the latitude and longitude of the surface of the Earth, and as time goes on, it gets bigger and bigger. And maybe I'll show you an expanding universe on the non-flat, the positively curved one here, and we'll see if this works. So this is, it's going to take a little time to fill up, so we'll let it run for a bit while I keep talking. So this has positive curvature. And we also have open geometry, and that has to go out to infinity on both sides also, and that has negative curvature. So over here, like I told you, the galaxies are held together, so they're stuck on like these red dots, and all you can do is, I think it's leaking a little bit up here, so maybe if you want to hold this, that might be a little bit easier. Because this pipe is getting deformed. Okay. So the galaxies are these red dots, and you can think of yourself as an ant. All you can do is you can walk on the surface over here, and you cannot come out. There's nothing outside. There's nothing inside. And you should just ignore this neck. So it's a perfect sphere. There's no obvious center. And sitting on any galaxy, there's space being created, and they're moving apart from each other. So if we start over here and look at the nearby galaxy over here, that light coming to us takes not that much time to get to us. So if it starts out blue, it'll still be quite blue by the time it gets to us. But if we go to this galaxy, it takes longer, and during that time, more space is created, and that light starts developing a little bit of a purple tinge, and a further away galaxy over here, it takes longer, and it takes longer, and so the further away the galaxy is, the redder it is. So every galaxy moves away from every other galaxy, and there's no center, and this is the expansion of the universe, and I think we can just stop this now. So we can move on to this. So the scale factor in this case very loosely can be thought of as the radius of this sphere. And so we know that Einstein's general, you can probably just put it on the floor. I think it'll be fine. It can run out. You can even disconnect it. Is the dynamical variable is the scale factor. And what causes the expansion is the gravitational field, and that's powered by the energy density. So I'm going to talk about the expansion of space locally, because we don't want to talk about the whole universe, because the mass there is infinite, and it makes things very difficult when you're dealing with infinite quantities. So we'll look at a little region of space and see how things change there. So we know, so dot means the time derivative of the rate of change, or the speed of the expansion. So we know that the speed of the expansion is positive, things are moving away. So it's like somebody started a car and she put her foot on the accelerator, or she started out and she moved away and she sped up, and then we want to know whether she has her foot on the accelerator, whether the expansion is going to accelerate, or she's put her foot on the brake and so it starts slowing down, and then eventually it stops. And the easy way to do that is to get an equation, an acceleration equation. And this is very, very similar to Newton's F equal to ma. It's written in the form A equal to F over m. And it's very, very unfortunate that in Newtonian physics one calls the acceleration A, and in general relativity one calls the scale factor A. So I'm never going to use A for the acceleration here. I'm not going to use it anywhere for acceleration. For acceleration, I put 2 dots on top. It's the second time derivative. So this is acceleration is equal to force divided by mass. And because I'm looking at a little volume, a little part of the universe, I'm going to add up all the mass there and divide by the volume and get a density. And that's why I have a density over here. And there's also a pressure, and I'll explain that. We'll ignore this for a minute here. So there's a big G over here because gravity is determined by Newton's gravitational constant, but this is Einstein's Friedmann equation that comes out of general relativity. And we have a minus sign over here. And so this is the density, it's the mass per unit volume, and there's a minus sign. And so we can kind of think about what would happen if we ran this a little bit and looked at nearby galaxies. So if we look at 2 really close by galaxies, and they're close by enough, then Newton would tell us that their mass is going to be attractive and they're going to want to pull on each other. But Einstein's going to tell us he wants to create space here and push them apart. So depending on how much mass you have, if this rho, which is the mass per unit volume, if this is very large, this minus sign is telling us that there's going to be a deceleration. So the Big Bang happens, things start moving apart, and then eventually things start getting pulled together by the gravitational force due to the mass between these guys. And so we can also make use of the fact that these galaxies actually move on the surface here. So they have some kinetic energy, and this guy is just the rest mass energy, but because they're moving on the surface, they have some kinetic energy. And Einstein told us that for any source of energy, E is equal to mc squared. So m is equal to E divided by c squared. So even the kinetic energy can give you a mass that will act like a source of a gravitational field. And that's just pressure. So things moving have some kinetic energy and they act as a source for the gravitational field. That's why there's a P over here, and that's a relativistic effect. So if you have galaxies that rest on the surface, they're going to try to slow down the expansion. You have galaxies that are moving, they're going to slow down the expansion because of this minus sign. So you're very happy and you go tell your astronomer friends that you're going to predict the acceleration is going to be negative, things are going to decelerate, and so the universe is going to expand, it'll get to a maximum size, and then it'll start contracting. And so they go out there and they measure A double dot, and they find that it's actually positive. And so then you have a problem. So you have 2 options here. You could say Einstein's equations are wrong, and so we throw this away, and so it's not a problem that A double dot is positive while this is predicting it's negative. But we know Einstein's equations work very well for black holes. They work very well for gravitational waves. And so you don't want to throw them away if you're conservative. And so you try to introduce a new substance, which you call a cosmological constant. And it also has a rest mass piece, and it has a part that's associated with the pressure. But it's got a very strange equation of state. It doesn't have a positive pressure. It has a negative pressure, and its pressure is minus the energy density. So everything inside these round parentheses here, you can replace the P with minus rho lambda, and that'll give you minus 2 rho lambda. And if you make rho lambda much bigger than rho matter, this negative piece will dominate over this positive piece, and then everything inside the square parentheses will be negative, and that negative sign will cancel this, and it'll give you a positive acceleration. And that's what dark energy is introduced for. It's this hypothetical substance allowing you to preserve general relativity and be consistent with the measurement of a positive acceleration. And this would be a very silly thing to do, except for the fact that you can measure rho lambda through maybe half a dozen different experiments, and they all give you roughly the same kind of rho lambda. So that's telling you that probably there's some dark energy out there and we need to do better observations and more detailed observations to test this idea more carefully. And I'll just stop here because I've run out of time and I'm happy to answer any questions people have. Thank you.
Thank you for the talk, sir. Very
Thank you.
informative. My question is, what exactly is the fabric of space-time made of, and what exactly makes it to expand?
Okay, so there's no fabric, it's not a physical thing, it's just a solution of Einstein's equations of general relativity. And what makes it expand and contract is it's basically gravity. So it's gravity, and that gravity is created by whatever mass, that whatever objects live in this space-time that you're talking about. So it's this whole idea of a fabric and everything, it's introduced to describe in words what you get from solving Einstein's equations for general relativity. And it's a very loose way of describing something that you could more precisely call the metric tensor. And part of the metric tensor for cosmology is the scale factor. So if you want to loosely think of the scale factor as being the fabric, you can do that.
Sir, my question is about, as we know, we detect the gravitational waves using lasers, and its sensitivity is about it can detect the sensitive gravitational wave on the 1,000 diameter of a proton. So that much sensitivity is there. So if the universe is expanding, if that is the problem, that also affect the detection of the gravitational wave. That parameter is also included.
Yeah.
Then can we detect the expanding universe in not observing the galaxies like redshift or blueshift, but on the Earth? Is there any devices that can we can devise so that we can detect the expanding universe?
So without using light.
Yeah.
So right now, light is the only thing, but hopefully first with gravitation, with neutrinos and then with gravitational waves, eventually we'll be able to see this expansion also. So we can see distant objects in gravitational waves, but the expansion is, so that you can kind of think about the time scale of the expansion. So the universe roughly doubles in size every 13 or 14 billion years. So if you want to talk of that compared to the time scale for visible light, so that's roughly of order, we're talking about a femtosecond, the time period of visible light, right? So the ratio between the time of a light wave oscillating and the time of the universe doubling in size is 33 or 30 something orders of magnitude. So you have to be able to measure things to that kind of precision for gravity waves to see the redshifting because of the expansion of the universe, and we can't do that now. So we can barely just detect these gravitational waves. So a more possible thing is with LISA. I don't know if you're familiar with LISA. So LISA is this experiment mostly by the European Space Agency. They're going to put 3 satellites in a triangle in space with a much, much bigger distance between them than LIGO. And so they should be able to see much shorter wavelength gravitational waves. And they're hoping to see remnants of gravitational waves from the early universe. And maybe in 20 years, 15, 20 years, if it gets built and that happens. But we have a better expert here who can answer questions about gravity waves.
So does that affect, so that parameter affect, the expanding universe
It affects gravity waves provided they're coming from large enough distances. I mean, for gravity waves from if you can get 2 black holes to merge or 2 neutron stars to merge in our galaxy, the expansion of the universe won't affect those. So it's got to be...
how they compensate?
How does it compensate?
If that parameter affects,
Yeah.
how they compensate while detecting the gravitational waves?
It'll reduce the amplitude of the gravitational wave, just like it reduces the amplitude of the electromagnetic wave. And so it decreases it, but the time scale is very, very different, and so it's very gradual.
Okay. Thank you.
Thank you.
Hi sir, good evening.
Hi.
So my answer is same about space-time. So does the space or space-time exist before Big Bang? If yes, then how? Because this observable universe exists after Big Bang and space too.
Okay, so it depends what you mean by the Big Bang. So in the 1960s, the Big Bang started happening maybe when the universe was a fraction of a second old. And so if you call that the Big Bang, then we can go back even further now. So now we can go back to when the universe was maybe 10 to the minus 33 seconds old, and that's when inflation is thought to happen, and space-time exists then, and we can write down general relativity equations, and everything is okay mathematically, and we can describe inflation consistently mathematically using general relativity. So we can make predictions about inflation. We can make predictions about what the universe was doing when it was 10 to the minus 33 seconds old. And those predictions are not inconsistent with the observations now, but the observations aren't good enough to test those predictions well enough yet. So we don't know if inflation really happened or didn't happen. So if your definition of the Big Bang includes inflation, then it's very difficult right now to go much beyond inflation. In principle, we could go back another 5 or 6 orders of magnitude in time to something called the Planck time, when we can still use general relativity. But before that, at the Planck time, or even 10 or 100 times bigger than the Planck time, quantum fluctuations are too big, and general relativity, we don't know how to make it consistent with quantum mechanics. So when you get to times when the universe is maybe 10 to the minus 40 seconds old, we don't know what's happening there because we don't have a consistent mathematical description that we can use to describe the physics at that point. So up to about 10 to the minus 35 or 10 to the minus 40 seconds, we have space-time.
Thank you, sir, for the talk. I have one question that's a follow-up of what a friend asked. If the fabric of space is just a representation of what Einstein's equations are, then what exactly are we detecting when we have, say, gravitational waves? Like, what exactly is it? Energy? What is exactly?
So you can kind of think about electromagnetic waves first, right? So there's an electric field and a magnetic field, and the electric field is oscillating, the magnetic field is oscillating perpendicular. And so you're familiar much more with sound waves, right? So there you can actually see the energy. So stuff rises and falls, or even if you're hearing the sound waves, listening to a big speaker, you can feel your body move back and forth. So you're seeing the energy, or the kinetic energy of you, you are the detector of that sound wave. And so it gets transformed into that kinetic energy, and you detect it that way. So the same thing can happen with electromagnetic waves. So you have charged particles, and they can move the charged particles, and then they eventually become kinetic energy, and so that's what you're detecting there. And that's what's happening with the gravitational waves. They're just stretching the fabric of space-time too, and you have these big masses, and so because the fluctuation in the gravitational potential, they'll move these masses around, and you can see them in some sense as the kinetic energy in those masses, because those masses have mirrors, and so the lasers are measuring the distances very precisely between them, and they can see them move, and that's what you're measuring.
Thanks for the talk, Professor. So my question was about
dark energy and dark matter. So I've always seen them together.
Yeah.
Are they different manifestations of the same thing, or are they actually different?
They're different. So I don't know how much time we have, because I have a few slides I can do dark
Okay.
matter also. So we have this equation over here, and so we want to figure out what to put in. So there's an M here for matter. And if we look at the energy budget at the present time, that M has two parts. There's the 5% over here and the 25% over here. So the 5% here is what cosmologists call baryonic matter, and that's the name they give to atoms and molecules. And this number started getting pinned down in the 1960s. It's everything that's made up of atoms and molecules, so humans and blue whales and elephants and planets. And so the way this gets measured was through some of the theoretical work done by Gamow and his graduate student Alpha and his postdoc Herman. They were motivated by a computation that Chandrasekhar did, I think, with Hendrik in 1942, where he wanted to start explaining the abundances of the light elements. And he started out by doing this in an equilibrium expanding universe. And he found that he couldn't explain the abundances. And then Gamow realized that at some times during the expansion will be too fast and things will go out of equilibrium. So he started doing the computation over again in a non-equilibrium expanding universe. And so when things are very hot, you don't have atoms, you don't even have a nucleus, because you break it down into neutrons and protons. And so you have protons and neutrons and electrons. And when it's very hot, it's just protons, neutrons, and electrons. But sometimes two neutrons or two protons, or a proton and neutron, can be moving right towards each other. And if they get close enough, they can... the kinetic energy can overwhelm the strong Coulomb repulsion between the charged particles enough to get them close enough for the strong force to pull them together, for them to fuse. So we know that there's got to be a much, much stronger force than electromagnetism, because if you look at the nucleus of an atom, there's a lot of protons there, and those protons are pushed apart by the Coulomb force. But nuclei are stable and for a long time. So there's this strong force that only applies when the protons get very close together. So they studied this fusion process, and they made up the light elements, and they did the nuclear physics reactions. And they realized that there would be electromagnetic radiation emitted. And through a very inspired guess, they ended up saying that this would be in the microwave part of the spectrum, with a temperature of maybe 10 to 20, I think 20 Kelvin. And people look for this. So they did this in the mid-1940s. And people tried to look for this. And even the guy who invented the microwave detector, the Dickey radiometer, Bob Dickey, he pointed his radiometer at the sky. This was invented as part of the radar program for World War II. And he got an upper bound on this microwave background, which was discovered by accident by Penzias and Wilson at Bell Labs. And the explanation was provided in this paper by Dickey, Peebles, Roland Wilkinson. And by the 1960s, once you got the temperature, you could figure out that 5% of the stuff out there was atoms and molecules. Even before that, Zwicky was looking at clusters of galaxies where these galaxies are orbiting each other. And from the Doppler effect, he could figure out how fast they were moving. And he said if this motion is caused by Newton's gravity, then he can figure out how much mass he needs to cause those speeds that he's seeing. So he computed the mass. And from the mass he computed, he compared that mass to the mass in the stars and in the shiny stuff. And he found he needed much more mass than he could see in the stars. So that was the first indication that there was some dark matter out there. So he was measuring these galaxies moving around in orbit around each other. And they move at the most at a few thousand kilometers a second, which is very, very slow compared to the speed of light, which is 3 times 10 to the 5 kilometers per second. So this motion is non-relativistic. And physicists call that cold because it's not moving very rapidly. When you heat things up, they move rapidly. So Zwicky didn't know that only 5% of the stuff there was baryonic, and he didn't realize he had discovered non-baryonic matter, and it's now known to be about 25%. And this was this number started to get established in the 1970s through the work of Vera Rubin and other collaborators, where she was looking at the rotation curve of spiral galaxies. And more recently, people have discovered this substance which they call dark energy. And this is a very unfortunate choice of words, because it's not energy in the sense of mechanical energy or nuclear energy or chemical energy. This is just energy to distinguish it from the matter. So Zwicky's matter had to be dark because he couldn't see it there in the stars. And this stuff also has to be dark so it doesn't emit or absorb light. But if it was made up of particles, these particles would be extremely light, and they'd be moving at speeds very close to the speed of light, so they'd be moving relativistically. And they're also not made up of atoms, so they're non-baryonic. And this is the biggest contribution to the energy budget now. So this was suggested in the 1980s, and this is what was, so you predict accelerated expansion when you have dark energy. And the supernovae measurements in the 1990s measured this accelerated expansion. And if we have time, we can talk more about that. But basically, we don't understand 95% of the stuff out there. And we have some idea of this stuff, which we spent the last 400 years studying. So if there's other questions, I'll be happy to.
We have time for 2 more questions from here. Thank you, sir, for the amazing talk. I have 2 questions. Does the scale factor change over time? Because you have shown two or three lines over there. So does it change over time?
Yeah. So if we look at, well, I guess, so we can, so there's matter, right? And there's radiation also. So matter, maybe I'll just back up over here. So matter, if you measure the density of matter, it's a rest mass energy divided by the volume, if you're looking at a little cube over here or a sphere. So if it's rest mass energy, that doesn't change with time, but the volume changes with 3 factors of the scale factor. So the density of matter drops like 1/8 cubed. And if you measure it now, it's a few times 10 to the minus 30 grams per cubic centimeter. But there's also, so that's a picture of Zwicky, and he's the guy who kind of introduced dark matter. Excuse me. This is the KAAPI satellite, the first satellite that measured the spectrum of the microwave background. And this is a picture of the spectrum of the microwave background, the intensity here as a function of wavelength. So short wavelength light is over here, long wavelength light is here, blue and red. And these are the data points with error bars. And this is a fit just to these data points. It's called the Planck spectrum. And this is a very special type of spectrum. It's a black body spectrum. It's if you have a body that's perfectly black and you heat it up, this is what its spectrum will look like as a function of wavelength. And the temperature at which this thing peaks, in this case, is it's at about 3 Kelvin or 2.725 Kelvin, and that corresponds to about 2 millimeters wavelength. So for, if you know it's a Planck spectrum, then you know that the intensity or the energy of this system obeys what's known as the Stefan Boltzmann law. I don't know if you're familiar with that. So that's this law over here. The energy density goes like the 4th power of the temperature. And we know from Mr. Boltzmann that the energy in the photons of this kind of light is Boltzmann's constant times the temperature. And we also know from Planck that the energy is proportional to 1 over the wavelength, or it's proportional to the frequency, and h is Planck's constant. Since you have 2 formulas for the energy, one's from Boltzmann, one's from Planck, you can equate them. So you know that the temperature is going to be proportional to some constants, Planck's constant, Boltzmann's constant, Planck's constant, and the speed of light. And so the temperature is inversely proportional to the wavelength. But as I showed you from the stretching, the wavelength goes in proportion to the scale factor. So the temperature drops like 1 over the scale factor, and the energy density in the radiation drops like the 4th power of the scale factor. So the easy way to think about this is to think about Einstein's mass here. So this is a relativistic system, and it's coming from the wavelength. So it's E divided by C squared divided by volume. And so from E being proportional to 1 over lambda, you get 1 extra length scale in the denominator. So it's 1 over lambda to the 4th. So if you plot these guys, so this is the density and mass here on a log scale, and this is the age of the universe, or the scale factor. So the scale factor gets bigger as you go over here, so we live over here now. So the blue one is the 1 over A cubed in the rest mass of the matter, and the red is the radiation, the 1 over A to the 4th. So the densities change, the scale factor changes, and I'm not plotting dark energy here. But if I did, and I plotted a cosmological constant, I can go back and talk about how the dark energy was measured. It would be this green line over here. And so you've got to realize this is a log-log scale. So it looks like the green line is hardly above the blue line, but it's actually about a factor of 2.5 or 3 above it. And it's dominated for about half the age of the universe. So over here, radiation, photons dominate, then dark matter and ordinary baryonic matter dominates, and dark energy dominates. And maybe I should stop here because I'm getting in trouble, but I'm happy to talk more if people have questions.
So, good evening and wonderful talk.
Thank you.
So, my question is regarding where exactly is the current science in the path of identifying dark matter? And does antimatter have any role in the expansion of the universe?
So you want to know how much progress has been made finding dark matter? So far we're just seeing the gravitational effects produced by the dark matter mass. And so sometimes it's useful to go back a little bit into the past where we've seen similar problems. So if we go back to the 1930s, when people were doing scattering experiments, they were seeing that energy and momentum were not being conserved. And this upset Pauli and upset other physicists quite a lot, because they had this idea that we have these theorems about conservation of energy and momentum, and we might want to preserve them. And so Pauli suggested that some of the energy and momentum was being carried away by an extremely weakly interacting particle, which came to be called the neutrino. And so he did this in the 1930s, and it took a quarter of a century before Reines and Cohen and others were able to detect the neutrino because it interacted very, very weakly. And so dark matter is introduced to preserve Newton's inverse square law of gravity on scale of galaxies. And we know that it works really well on the scale of solar systems and even on scales bigger than the solar system. And we don't want to try to disregard it and discard it. And people have tried to explain Zwicky's observations and Rubin's observations by changing the inverse square law, and they can't do it, it doesn't work. And they've also tried to do that by changing F equal to ma, that goes into the description of the discovery of dark matter. And they've succeeded in that partially through this formalism that's called MOND, Modified Newtonian Dynamics. And so what people say there, and this is a guy called Milgrom, so he says F equal to ma is correct for stronger accelerations, but when you get down to extremely weak accelerations, F is not proportional to A, but it's proportional to a function of A. And he finds by choosing different function for each galaxy. He can get rid of dark matter on the scales of galaxies, but he can't get rid of dark matter on the scale of clusters of galaxies that way. And so this is kind of a digression, but if you want to preserve Newton's inverse square law of gravity, you have to introduce dark matter, and it's not visible, so it's got to interact very weakly with electromagnetic radiation, and we haven't discovered it directly. So there's a lot of experiments. So one set of experiments is going to be at particle accelerators, and they've been ongoing for a while, like at the LHC at CERN. So again, you're going to look for disappearing energy and momentum. And the other experiments are these deep underground mines where you do the same kind of things you do to detect neutrinos. You try to shield it from cosmic rays, and you build things where maybe a dark matter is going to trigger something that you can detect either ballistically or through the light that's emitted. And people are just going to build bigger ones and more sensitive ones, and hopefully we'll detect it. And we do know too, we know neutrinos and they behave like dark matter, but they don't give us enough of the dark matter we need.
Yeah. So even Large Hadron Collider, when we are talking about, there are like the presence of antimatters.
Oh, that's right. Okay. So antimatter, there's not a lot of antimatter on the scales of cosmology. So there are experiments. So one thing you might be interested in is whether antimatter behaves in an opposite way gravitationally than matter. And I mean, that might be a very nice thing to do, because Einstein says that the gravitational field is going to be proportional to the mass. And so people have actually tested this, so they've created, so the problem with antimatter is you create charge, if you create positrons, they have electric charge, and they get affected by stray electric fields. And so you want to figure out how things behave in gravitational fields. It's not good to use positrons, because any little bit electric field anywhere is going to cause problems. But people have created anti-hydrogen, and they studied how gravity affects it, and it affects it the same way as it affects hydrogen. So antimatter, we know, is not very common on large scales, because if it was, it would interact with matter and produce gamma rays, and we don't see lots and lots of gamma rays all over the place. So it's not a big contributor to the energy budget of the universe.
So we have a large online audience, and I picked one question from this. One is this is a slightly more advanced question. So the question is, how do we know that the scale of the baryon acoustic oscillations is consistent with that of the CMB?
How do we know? So they're just asking for the acoustic sound scale. How do they know they're consistent? I mean, we can measure both of those, and the baryon acoustic oscillations are consistent with what the CMB predicts.
Perhaps for
so
the audience,
so the CMB in the, if you look at the power spectrum of the CMB, you can see peaks and troughs, and I don't have it on these transparencies, and those allow you to measure the scale of those acoustic wavelengths. And for the baryon acoustic oscillations, because you're actually measuring also the dark matter when you measure the matter power spectrum, but only the baryon part, which is the leftover from the protons and the electrons, that is what interacted with the acoustic waves at early times. It's a much, much weaker signal in the power spectrum of the galaxy distribution, and they're consistent with each other. So you can fit the galaxy observations and leave that as a free parameter and extract that length scale, and it's consistent with what you see in the microwave background oscillations.
Okay, I'm sure there are more questions, but for the interest of time, let's break this formal session. And of course, Professor Ratra is available for some more time.
I'm happy if there's lots of people, I'm happy to just continue this way, whatever you
so
want.
we can have that conversation over copy, and that is the idea of this lecture series. So feel free to talk to him at your along with the coffee. So
And you're welcome to take these cards and look at that website, and if there's any left, I'd appreciate them back.
If you're not registered for our emails and you want to be registered, subscribe to our emails, please just come to me outside and I'll have you registered for our future emails.
Okay, yeah, so this is, so let's conclude the sessions formally. Let's thank Professor Ratra for giving this wonderful exploration of this, the universe. And as Devduta mentioned, this is a monthly lecture come discussion series, but ICTS also has several other outreach activities and further other activities for students and young researchers. So if you're interested in keeping in touch, please sort of contact the desk outside, and so you can register your email to get subscribed to our mailing list. You can also follow us on our social media. We are on Facebook, Twitter, just now X, Instagram, and LinkedIn. So please subscribe and follow us. So let's thank the speaker once again, and please join us for a coffee.